Good afternoon. I'm Donald MacVicar from ActBlade. At ActBlade, we make extensive use of Abaqus and its automation options through the use of Python scripting. But firstly, a small introduction to ActBlade. At ActBlade, we're tackling the challenges of the wind energy industry. The wind energy industry is on a mission to reduce costs. To achieve this, larger turbines and thus larger blades are required. With current technology, wind turbine blades become very heavy, with challenging and long production processes. At ActBlade, we're developing a lighter solution with more flexible and less costly manufacturing. The ActBlade. The ActBlade is an assembly of components with a composite spar as the main structural element. This and then a set of other components that support a textile that's under tension, which forms the outer surface of the blade. Here we can see our prototype undergoing fatigue testing at the Ori Catapult Test Facility in Blyth. We are aiming to test our blades on a real turbine in Q1 next year. In our design process, we have two major areas where we make use of the power of Abaqus. Firstly, for the structural analysis of our composite spar, where we're looking to solve questions around global deflections. These are large structures. Currently, we are working on a 49-meter long design, which will deflect by up to 10 or 12 meters in extreme load cases. Buckling and fatigue are of significant interest to us, and particularly through early phases of the design process. The second area we look at is fluid structure interaction, or FSI. As our blade is a textile for the outer surface, this is very flexible and deforms due to the aerodynamic forces acting on it, as well as the global bending of the blade. This behavior is extremely complex and difficult to model and affects the aerodynamics. With our fluid structure interaction solution encompassing Abaqus, we're not only able to predict the aerodynamic output from the blade in terms of lift and drag, but also reverse engineer the design shape so that we can optimize operational performance. If we first take a look at the structural analysis tools, here we have built a system to make use of parametric CAD from Grasshopper to fully create Abaqus jobs with all properties, load application, ready for running. This is carried out using about 840 lines of Python code, which fully automate the model creation process, where geometry comes from step files with ply layups, job definition, material data, and loads coming from other supporting CSV files. The main Python script then takes this information and creates a set of scripts that are then executed in Abaqus using the run script options, which then in turn generate the model and the jobs ready to be executed. If we look at a little detail of each of these steps, so first we import the geometry, which comes from in the form of step files. Our part is split up into a number of surfaces that have common ply structures within them. These surfaces are then sliced at all ply drop locations, load points, and other areas of interest along the length of the spar. We then apply layup as a composite layup. This can have hundreds of different panels within a single blade. We then automatically create the mesh using seed points along common edges to ensure, and the slicing, along with the slicing, ensures we have a regular mesh and a structured mesh that matches from geometrical element to element. We also then apply the coupling and other boundary conditions as required for a particular load case. And then we're ready to run the model. We usually run the models manually and do manual post-processing to extract the relevant results. If we then move on and have a quick look at our fluid structure interaction analysis, here we have two main Python sections again that are the scripting parts that do the work. The first part is for model creation, taking airfoil geometry, material data, and other properties. Again, through Abaqus run script options, we then create the model, and the other part is the FSI loop itself, where we couple Abaqus with Xfoil to perform the fluid structure interaction analysis. We've also validated this process and the analysis using wind tunnel testing. Looking more closely at the model creation part of this, we take a 2D airfoil sections, usually from a CSV file. This then gets extruded to form the external surface. From that external surface, we slice it up and create the internal part, so that the spar and other relevant features that we have to create the structure. And from that, we have to then create contact definitions between the different elements, which are, in our case, very complex between the textile and the internal supporting structure, that we have to model it in a very accurate way to capture the behavior of the textile. And from there, we then have a model ready to run where we take in the aero load as a CSV file and are able to run that model. And so that's us with our model ready for the structural analysis. If we then take a look at the fluid structure interaction section itself, where we couple Abaqus with Xfoil. Here we use Abaqus. The initial run through the FEA will be to apply the initial tension or pre-tension to the textile, so to get it into a tension state before we then take that deformed shape, run it through Xfoil to get the aerodynamic pressure distribution on this tension shape, and then we apply that as a surface pressure map through Abaqus again, creating Python scripts on the fly with other Python, calling Abaqus through the CAA system to run the script to generate a new model and then carry out or to run that simulation. From that simulation, we get a new deformed shape, and we can then go back around the loop, carrying out another iteration of aerodynamic analysis and feeding that new surface pressure map back into Abaqus again, and so on. And this process is repeated until we find the equilibrium, which we usually look at the aerodynamic properties have stopped changing, and usually that takes 2, 3, or 4 iterations of this process. And the result is that we get the aerodynamic performance of the textile blade and its deformed geometry and shape, and we can see how well our various features of the structure and of our blade are actually performing. If you look at the benefits of automating this design process elements for us, well, from the structural design perspective, it allows us to do fast and frequent evaluation of design options, and also look at these different options and different variations with a very detailed level. So we can very quickly evaluate different ply layups, different structural options like different core materials in a very automated and structured way. From the FSI simulation side, it allows us to evaluate the complete blade performance through a number of aero cases with different airfoils in different places along the blade. We can calculate that very quickly and in a very efficient process. And that allows us to then introduce those aerodynamic loads into the design chain early, particularly when we're simulating the full turbine behavior. We can account for the textiles behavior into that global modeling at a very early stage. Currently, we're working on further extensions to this, where we'd like to improve upon our current work, where we're looking at mostly on the post-processing automation side, being able to create templated reports, so inserting plots and captions and standardize the output so that we get a nice, clear, consistent results and make things more easily and more automated in terms of comparing different results. And then the other one is combining the two, the large structural model of the spar with the aerodynamic model and all the features of the textile into a full blade model that we could then simulate through the fluid structure interaction loop as well. Why we chose Abaqus and why we work on automation? Well, the main reasons there are really that with the automation, it helps us reduce the errors by minimizing manual entry and handling of data. The Python script options within Abaqus are really suited very well to the work that we're doing and is generally pretty easy to use. They enable us to do a quick turnaround for parametric studies and explore different design options and enable us to have an algorithmic approach to FEA-driven design tasks. And For us, for using Abaqus is essentially using a well-established and trusted FEA package so that we have good levels of confidence in our results as quickly as possible. Well, thank you very much for listening. And I will be happy to take any further questions in the chat session. Thank you very much.